Good afternoon, everybody. Welcome to the latest iteration of ICN2's Nanoseminar series. So today our main talk will be given by Professor François Léonard, who's a researcher at Sandia National Laboratories in California. But before that, we'll have an introductory talk from Sebastian Castilla, who is a postdoc at ICFO. I understand he just got his PhD a few months ago, so congratulations on that.
Thanks.
And now a postdoc in the group of Frank Coppens, I believe, right?
Yeah.
Same group. Great. So Sebastian will talk for around 10 minutes or so. If you have questions, you can put them in the Q&A or in the chat with the options down at the bottom of the Zoom here. Or if you want to ask a question and have your mic activated, you can also raise your hand. And then I think the hosts here can turn on your mic and allow you to ask directly. And if you want, you can also ask questions of Sebastian after both talks are done, or you can chat in the chat while the talks are going on, however you wish. So with that, Sebastian, the floor is yours. Go ahead.
Okay. Thanks, Aaron, for a very kind introduction. Also, thanks for the organizers for inviting me to giving this talk. So I will speak about electrical detection of high quality 2D Polaritonic mid-infrared nano-resonators. So since it's a very short talk, I'll just give you a flavor about this topic. And so I will skip the jokes I have in the slides prepared, but so I just go to the main things. So for the people that are not very familiar for the photonics field, basically we are, this is showing the light spectrum, and we are focusing mainly on the mid-infrared range, which is basically the range between visible and millimeter wave. And this range is consisting of wavelengths in the order of from 5 to 10 micrometer. And in particular, is interesting because most of the objects emit this type of light at room temperature. So this leads to a lot of applications such as gas leakage, where you can see through mid-infrared cameras, you can see the gases that you cannot see with your bare eyes, or you can also track the temperature profile of fast-moving objects or for high-resolution thermal imaging. So the way that this range is linked with the 2D polaritons, so for the two-dimensional materials, basically is that these polaritons that consist on a couple excitations of charged particles with light, or also can be lattice vibrations with light. This takes, let's say, this occurs at the mid-infrared range. If you look at the permittivity of the HBN, you can see that the so-called Reststrahlen bands occur at this mid-infrared range. And these materials show very interesting properties, such as strong light confinement, where you can compress the incident wavelength into hundreds of times, and also shows longer lifetimes in the order of 20 picoseconds, which is several orders of magnitude compared to the metal counterparts. So these polaritons, therefore, has been used for molecular sensing, as you can see here in the case for HBN nanoribbons. When depositing very thin film layers of molecules, they can strongly change the resonance of these ribbons, and also reach to the strong coupling regime. And in the similar case, it happens with graphene plasmons, where also is modified this resonance with thin films of silk. So also these 2D polaritons has been exploited for photo detection. So in principle, this can also enhance the photo response. And in this particular case, in this work that we did some years ago, basically we place antennas on top of a graphene detector, and besides focusing the mid-infrared light at the nano gap of this antenna, also this launches the photon polaritons in HBNs, and as you can see, this X-ray-like propagation. This basically guide the mid-infrared light at the nanoscale and focus it onto the photoactive area. So if you look at the spectral response of these detectors, basically with different light polarization, if you're exciting the bow tie antenna or the other, you basically have enhancement of the photo response at the HPN Restrepo band, as you can see here. And if we look into the absorption enhancement spectra, that in this case is spatially resolved, if we, when the 0 is at the cap of the antenna or gates, you can see different interference pattern that is attributed to these phonon polaritons that is enhancing this response. And but you basically can improve this response even further if you tune the antenna length to be fully resonance in the HBN Restrepo band. So as you can see here, this increased significantly responsivity. So in the work I will present here, basically would be to combine the Polaritonic material and the detector in one single device. So in this way, we don't need an external detector to perform infrared spectroscopy. Also, it has certain advantages that is to constitute a very compact platform, and also that leads to room temperature operation, zero bias channel, and also without the need of patterning the material. So the device concept basically is we place metallic nanorods on top of a 2D stack, which is constituted by top HBN, graphene, and bottom HBN. Here's an optical image of this device, and also the CM images of these metal nanoribbons that we pattern. So we do experiments on these samples, basically transmission measurements, which are based on FTIR. And we observed that these peaks actually increases the amplitude of these peaks, and also blue shift, which means that it goes towards, the resonance goes towards smaller wavelengths or higher frequencies. And we in particular observed these two peaks that in the simulation show a very similar trend, and also the spectral position of these peaks. And if we look these peaks a bit farther, we observe that the PK corresponds to an hybridized polariton, where the phonon polariton HBN propagates across the whole 2D stack and constructively interfere with graphene. And in the case of peak B, just is a graphene plasmon that is just resonating in the graphene plane. So based on these results, we produce more devices in order to explore by photocurrent measurements. So we do spatial mid-infrared photocurrent spectroscopy, and we have that in this case we have a split gate that we can tune independently the Fermi level of each region. And we observed that when the graphene is uniformly doped, basically we observe that most of the signal comes from the source, from the electrodes interface with graphene. And when applying the proper gate voltages, we observe graphene PN junction. That is the dominant response. So if we locate at this position and measure the photocurrent map as a function of the two gate voltages, we observe multiple sign change of this photocurrent, and this is a fingerprint of the photothermoelectric effect. So based on this effect, we are able to electrically detect these polaritons, where basically we label here with different numbers. And in particular, we highlight also these green bands and also yellow one that corresponds to the upper and lower Strahlen band of HBN, and this one to the silicon oxide. And in particular, we observe how the peak here, blue shift, when increasing the Fermi level, that corresponds to graphene plasma, and also this one that is appearing at longer wavelengths. And when looking into the theoretical calculations, we observe a very good agreement with the experiment and theory in terms of peak position and relative amplitude. So we did more experiments on our devices, and in this case we focus on the Restrepo band of HBN, the upper one in particular. And we observe also multiple peaks, and just to give you an idea, here in the dashed line is corresponds to the spectral position of the initial peak that at low Fermi levels, and when increasing the Fermi level, we see a blue shift of this peak labeled as 1'. And also we observe similar trend in the theoretical calculations. And Also, another way that we calculate independently was to do the dispersion relation through transfer matrix method. And we observe also that for the photon polaritons, the hybridized polaritons have multiple modes that they cross with the momentum that is given by the metallic nanorod array. So we have either the first or the second diffraction order mode, and we observe how this has good agreement with the experimentally observed peaks, the spectral position of them. And in the similar way, we did with the lower Strahlen band. We observe also these two main peaks that also are observed in theory, and similar exercise we did with the dispersion relation as shown here. And also just want to give you a flavor about the Q factors that we obtain for these devices. Basically, we reach values up to 200 or slightly above, and basically these are mainly contained in the Strahlen bands of HBN. And here you have that the graphene plasmons outside the Strahlen bands, they don't reach a value of 50, so they were a bit smaller due to ohmic losses. And with this, I would like to conclude my talk, that we have electrically detect these 2D polaritons, mainly graphene plasmons and hybridized polaritons. We have measured them through optical and photocurrent spectroscopy measurements. That we have also geometrically tuned this platform by changing the grating period and also the HBN thicknesses, and we can actively tune it by tuning the graphene Fermi level. And this can lead to selective detection in the infrared range, and also can lead to certain applications that I'm listing them here. So with this, I would like to also acknowledge the people that has contributed to this work, mainly people in Frank Koppen's group at ICFO, and the theoretical support from Eleftherios Liorikis and Nuno Perez. Thanking you for your attention.
Thank you very much, Sebastian. I don't see any questions in the chat yet, but if anybody has a question right now, they can raise their hand and their mic will be opened. I guess I'll ask one naive question real quickly. Sure. So how does, in terms of designing a photodetector, how does your graphene HBN heterostructures compare to just graphene itself? Because I could see some enhancement of absorption with the HBN, but then also faster losses if you do a photothermoelectric type of device as well. So can you comment?
So you mean the losses by the hyperbolic photon polaritons, right?
Exactly. Yep.
So in principle, yeah, what can happen is indeed that the cooling length of these hot carriers will be smaller. So you have to consider indeed for maybe the source drain distances to adjust to this. So indeed there's this interplay. You have enhancement due to longer cooling length or enhancement through absorption. We didn't play with these two parameters since we mainly use HBN, but definitely it's interesting to explore. Yeah, definitely an interesting direction. Yeah.
Thank you. Thank you.
You're welcome.
Anybody else? Okay, looks like not at the moment, but I'll remind that during this whole session, if you have further questions for Sebastian, you can put it in the chat and ask later, or he can answer directly through the chat as well.
Yeah.
So thank you.
Thanks.
Okay, so now we'll go on to our main speaker, François Léonard. So François is a distinguished member of the technical staff at Sandia National Laboratories in California in the materials physics department. He's one of those rare physicists who does theory and experiment, both, focusing primarily on nanoelectronics and nanophotonics, as well as fundamental properties of nanomaterials and their applications. He's a fellow of the American Physical Society, and he also wrote a textbook called The Physics of Carbon Nanotube Devices. And around 10 years ago, I worked with him for a few years and I learned a lot, and I think we'll all learn a lot from his talk today. So, François, go ahead.
Great. Well, thank Thanks a lot, Aaron, for the very kind introduction. So a few years ago, I had the pleasure of visiting the Institute in person, physically, and I still remember very fondly that experience. So hopefully you're seeing my slides now. Somebody nod, yeah, great. So today what I want to do is tell you about a body of work that we've been doing recently to look at novel designs for single photon detection based on quantum and nanoscale systems. So this work is done by a group of researchers here at Sandia National Labs, and we're located in Livermore, California, so not too far from San Francisco. And I want to acknowledge funding from DARPA and the US Department of Energy. So the motivation for the work, sorry, my slide's not moving. Okay, so the motivation for the work is that single photon detection is really a critical enabling technology. So you see it across different fields. So for example, in high energy physics, it's really critical to detect all of the particles that are emitted during an event. And this could be through a collider or because of dark matter detection, for example. Single photon detectors are used in quantum key distribution. You can make beautiful LiDAR images using single photons. And this example here on the right shows you imaging of biological processes using single photon detectors. So the way that single photon detection is currently done is using different types of technologies and materials. So the most sensitive single photon detectors use superconducting nanowires, but you can also use avalanche photodiodes, photomultiplier tubes. But interestingly, it was recently shown that the human eye has the ability to detect individual photons. So a few years ago, Prem Kumar, who was a program manager at DARPA, put together this chart where he compared the performance of different technologies for single photon detection in terms of their different metrics. So the efficiency, the rate at which it can count, the jitter, bandwidth, and so on. And what was realized is that none of the existing technologies are able to achieve high performance in all of these metrics. So for example, a superconducting nanowire has very high efficiency, but the jitter is not particularly small. On the other hand, an avalanche photodiode doesn't have as high of an efficiency, but it can actually work near room temperature. So this chart then led to some fundamental questions about single photon detection. So for example, what are the fundamental limits to single photon detection, or what does physics tell us about that? And are there inherent trade-offs determined by physics between these metrics? And what is the best architecture for a single photon detector? And how do we go about designing such a detector? So what I want to do today in my presentation is first tell you about a new general modeling framework that was developed to start thinking about detectors from the ground up. Then I'll show you how from this we understand some basic principles of photo detection, and this leads us to novel designs for photon number resolution. I'll show you some initial experiments with molecular and nanoscale systems towards these types of detectors. And finally, I'll give you a recent example of designing detectors that can do high efficiency detection while also being able to tell us the energy of the incoming photon. Okay, so let's dive right in. So this general framework that we developed is based from basic quantum optics. And the way that we now think of photodetection is as some kind of quantum optical field, like a single photon, that is incoming into a detector. And this detector is going to create the interaction between the light and the matter is going to create an excitation. And that excitation is going to be amplified and lead to a measurement, in quantum mechanics sense. So I'll give you the details of this framework in a minute, but what I want to say first is that we developed this framework so it can handle really general situations. So general light fields like single or multiple photons. The detector can be made of atoms, molecules, 3D solids, and so forth. And we can even handle complex structures, for example, where you have multiple detectors that are simultaneously interacting with the photon field. Another aspect of this approach is that it is practical in a sense that it generates performance metrics, so efficiency, jitter, and so forth. And then finally, the other practical aspect of it is, if you have photo detection mechanisms that you're interested in and you'd like to know if it could be good for single photon detection, we feel like we have a path to mapping those mechanisms into this formalism. Okay, so at a very high level, like I was saying, we now consider the incoming light as a quantum state. And we think now of a photodetector as being an object that is going to be doing some operation or transformation on this quantum state. And this would be this operator here. And at the end of the day, we want to generate a signal, and that is what we refer to as a measurement outcome. So if we can describe the photodetector in this way, it's actually very useful because the metrics fall off readily. So for example, the efficiency is simply related to this measurement outcome. The dark count rate is related to this measurement outcome as well, and so is the jitter. Okay, so the question then is, how do we go about obtaining this quantity here? So the way that we do this is we describe the time evolution of the system, particularly the matter subsystem here, through what's called a stochastic quantum master equation. And this is for the density matrix in the matter subsystem. So the time evolution then of the density matrix here is simply related to the internal dynamics of that system. So that's just its basic Hamiltonian. Then there's the light matter interaction. And then there's the amplification that will take us from this small excitation into a larger measurable signal. Okay, so I'm not going to go into all of the details of the math on this, but the main point is that by solving this time-dependent equation, you can figure out how the matter subsystem will evolve in time when a single photon comes in. And this allows you, for example, to calculate the current that is flowing in the detector. And once you know this, you can decide if you detected the photon or not, and that's a measurement outcome. So this takes us back to this formalism. So with this formalism, what we decided to do is go back and look at how photodetection was historically described and how we could go beyond that. So historically, the way that photodetection is described is you have a photon field, you have an absorption process, and you have an amplification process. And these are usually considered as being sequential. And so what we wanted to do here is go beyond that and look at what we call fully coupled quantum detectors, where the photon field, the absorption, and the amplification are part of one whole quantum system, and they're all strongly interacting. Okay, so what I want to do is I want to start with a very simple example to show you how we apply this formalism and what it already tells us about the fundamentals of single photon detection. So I'm going to use a very simple example. So it's a two-level system, and there's a single photon that comes in. So we will excite the system from the ground state to the excited state. And then we will measure the occupancy of this excited state at some rate chi with an external system. So just to give you a potential physical representation, imagine this is a carbon nanotube and this is a molecule, and we're monitoring the transition of that molecule with the nanotube. So I'm showing you here in this plot one of many trajectories that we have simulated. So we send in gray this single photon light pulse, and as it goes through the system, you can see here that the occupancy of the excited state increases, and then it decreases as the photon passes. And so associated with this in red is the current that would be flowing through this object here. And you can see that it dips below a certain threshold. And so we call that a click. So we have detected that particular single photon. So we repeated the stochastic simulations, and we also did some analytical work to show that this type of very simple photodetector has an efficiency that is at most about 33%. And even if you try to monitor the system more strongly, hoping to get a more sensitive measurement, turns out that the detector gets worse, as you see here. Okay, so basically what we're seeing here is that what we call measurement back action is limiting the performance of the detector. And so measurement back action is simply that when we're trying to do this measurement on the system, you can think of it two ways. Either it quenches the absorption of the system, or you can think of it as injecting noise in the system. In either picture, what happens is that this is really a poor single photon detector. Okay, so what we learn already is that we can't make any type of optical absorption that's monitored as a detector, because that would have limitations. So another way then to come up with a better single photon detector is to realize that we need to protect this absorption from the measurement process. And we do this by introducing an incoherent transfer between this excited state and a shelving state that we call C. And so what we can then do is we can monitor this at will because of this incoherent rate, so that the measurement process is not going to affect the coherence of the state. And so turns out that, again, by doing tens of thousands of simulations and analytical work as well, we've identified this very important result where if you make the two rates equal, so the absorption rate and the incoherent transfer rate, and both of them are fast compared with the width of the pulse, then this is actually a perfect single photon detector. So it has 100% efficiency and no additional jitter. So this is an important result for two reasons. So first of all, it shows that from a basic physics perspective, it is possible to achieve such performance, but also this type of architecture will serve as the basis for more complicated architectures that I will talk about. And if you want to imagine what incoherent rate might look like, so this is a carbon nanotube functionalized with an azobenzene, and when the azobenzene absorbs a single photon, it changes its configuration. That would be one example of an incoherent transition. Okay. So of course, two-level systems are great to learn some basic physics, but that's not how we actually make photodetectors. So the next step in our work was to extend our formalism so we could handle systems that have bands. So either, quasi 1D, quasi 2D, or 3D systems. And so the main difference in the model then is that we have some bandwidth zeta, and we can actually show that the dimensionality of the absorbing system strongly affects the performance of the detector. So, for example, here I'm showing you 3 model density of states for a quasi 1D, a 2D, or a 3D system. And here I'm showing you the efficiency that we calculated for this system, for these 3 types of absorbers. And what you can see is that by having a band, the first thing that happens is that we can actually now have some bandwidth for the detector. It is no longer just at resonance that it has high efficiency, but it can maintain high efficiency over a certain bandwidth. And interestingly, it turns out that the most effective way to maintain bandwidth, to get bandwidth and maintain efficiency is to actually use quasi 1D systems as the absorbers. And so associated with this is also a change in the condition for ideal detection. So now the bandwidth of the absorber actually enters in this relationship. Okay, so this was just to kind of tell you about some of the fundamental things that we learn and some of the basic building blocks. Now what I want to do is talk about designing a much more complex photodetector that can do a very difficult function, and that is photon number resolution. So the challenge here is that you have a photon pulse that is coming to the detector, and that photon pulse might have 1, 5, 17 photons in it. And you want to be able to tell with very high probability exactly how many photons are in there, and you want also the detection efficiency to be very high. So just to illustrate how difficult a problem this is, imagine that you have single mode waveguides, and you're able to separate this photon pulse into individual photons going into separate waveguides. And then you have a very high efficiency single photon detector at the end of each of these waveguides. So if the efficiency of each detector is 95%, which is close to the best that can currently be done, and you want to detect 10 photons, your probability of being able to tell that you had 10 photons is only about 60%. So you could see that this puts really, really stringent requirements on each of the detectors. So the question is, can we come up with an architecture that would circumvent this problem? And so in order to do this, we looked at 2 things. So the first thing is that instead of looking at these macroscopic detectors, we considered the situation where you would have a number of small nanoscale sensors that are each within the wavelength of the photon, and therefore they're all collectively interacting with the photon field. So that's the first step. And then the second step is to design a new architecture for each of these sensor elements. And so I showed you before how this part was basically an ideal single photon detector. For photon number resolution, what we want is we want to make each of these elements available to detect other photons as quickly as possible. So what we need to do is we need to transfer the energy from this shelving state into another subsystem, and therefore reset each of the elements. And we can then monitor this other subsystem at will. I'll show you some more specific examples of what this architecture can look like. But if you do this, you can actually predict that such a detector would have really advantageous properties. So here I'm showing you a plot where it's the number of elements that are needed in the detector to detect a certain number of photons in the pulse. So, and we want to do this with 99% efficiency. So the dashed line is this simple array scaling. And so what you see is, for example, if you want to detect pulses that could contain up to 20 photons, then you need more than 250 detectors to do this. Okay, so the scaling is really very poor. So this type of architecture can actually substantially decrease that number of detector elements. So if the energy transfer rate is fast, then you can actually show that it would be less than, a few tens of detectors that would be needed to achieve the same type of performance. Okay, so what we learned from this is that there might be new approaches based on nanoscale detectors and engineering of energy pathways that could give us new functionality for photo detection. Okay, so how could this be realized physically? So we also did a more detailed calculation where we considered some actual materials. And one way that you could realize this is if the measurement system here consisted of carbon nanotubes, and those nanotubes would be functionalized with a molecular system. And in this case, I'm using C60 as an illustration. And then we need an absorbing system that will be coupling to this. And so I put this other semi-transparent molecular layer on top of it. So the idea being that the photons get absorbed in that layer, the excitation gets transferred to the other molecule, which is then monitored by the nanotube. And so one particular mechanism, for example, for this energy transfer is Foster energy transfer, and that occurs over picosecond timescales. And there have been demonstrations that the efficiency can be near 100%. So long story short, if we put in additional numbers for the properties of nanotube devices and so on, we can make a prediction that such detectors would be able to maintain 99% efficiency of detecting up to 12 photons in a pulse. And they could do it at count rates of a fraction of a gigahertz with dark count rates less than 1 per day or even 1 per year. And again, there's no existing technology that can even come close to achieving this type of performance. Okay, so I've tried to start from the very basics and give you a motivation for looking at these types of molecular nanoscale hybrids for photo detection. Now I want to show you some examples of experiments we've done in the lab to start looking at these types of detectors. So what we do is we work with carbon nanotube devices, and they're in a transistor configuration. So the nanotubes sit on SiO2, and they have a backgate and source and drain contacts. So here you see an AFM image of one device. So these are the source and drain contacts. And this particular device has aligned carbon nanotubes. The nanotubes here are about 99% semiconducting, and we have a few stray ones in this array. We also work with devices made with individual carbon nanotubes. And then in either case, what we do is we then functionalize the device with a molecular system with the idea of trying to mimic this type of incoherent transfer into a shelving state. Okay, so the first example of a molecular system that I'll use is bio-inspired. So as I said earlier, the human eye has been shown to be sensitive to single photons. And the mechanism by which the eye detects a single photon is that you have this molecule called retinol that sits in rods and cones. And when a single photon comes in, it changes its configuration from the cis to the trans configuration. Now, that very simple change actually triggers a whole biochemical reaction that eventually leads to the detection of the photon through a signal sent to the brain. And so we sought some inspiration with this, and so we looked at these azobenzene molecules. Azobenzene has a very large dipole moment, and when it absorbs a single photon, it changes its configuration from trans to cis. And associated with this is this very large change in dipole moment. And so we were hoping to realize this type of architecture where the absorption of the photon by the azobenzene leads to its change of conformation, and then the nanotube is basically monitoring that change through change of its conductivity. And because we're working in a transistor configuration, we can actually get gain in this case because the molecule is similar to having a change in gate voltage for the transistor. Okay, so the way that we do this is we have these nanotube transistors, and then we attach azobenzene into a pyrene linker, and we then attach the molecules on the surface of the nanotubes. And this is a result of a measurement for illumination with visible light. So first, in the dark, what you're looking at is the transistor characteristic of this device. So this is the current across the transistor versus the gate voltage. And this is a p-type device. It turns on at negative gate bias. And what you see is when we shine light on the order of a few hundred picowatts, then we see a significant reduction of the current. So with these devices, so far, what we've achieved is a gain that is greater than about 10 to the 4 at room temperature. So that gain, in principle, should be sufficient to allow us to detect single photons, or at least a few photons. But we haven't been able to reach that limit yet. And the reason is because of noise in the system. So what we did next is we said, well, perhaps we should be looking at other molecules with a slightly different mechanism. And so what we did is we then functionalized the nanotube devices with a very thin film of C60. So we evaporate a few tens of nanometers of C60. And the idea here is that the single photons, where they're coming in, they create an exciton. The exciton diffuses to the nanotube C60 interface, where it gets split by an internal field. So one of the charges gets carried away really quickly, and the other charge remains. And so that other charge then impacts the transport of the carriers in the nanotube. Okay, so there's again a direct analogy with this type of system, where now this incoherent rate is the dissociation of the exciton. And what we're really monitoring here is this additional charge that's left behind. Okay, so this system actually shows some ridiculously high responsivity. So this is a plot of the responsivity in amps per watt as a function of the incident power in picowatts. So what you can see is that we have very large numbers, 10 to the 5 at larger powers, and then as we reduce the power, you can see that eventually we're approaching very high responsivities. And this point, for your reference, corresponds to 100 femtowatts of light. So in other measurements, what we've shown is actually greater than 10 to the 8 amps per watt. And so that the gain in the system now is a whopping 10 to the 8. And the system is actually sensitive to the visible and the UV, as I'm showing you here, but also to the near IR. Okay, so with this type of high gain, then we can move from looking at what I would call like continuous or classical types of fields where we're talking about power density and so on, to situations where we have pulses of light that have, let's say sort of a countable number of photons, even though the count is still high. But here's an example of this. So we operate one of these array devices. And so this is the device in the dark. So you have very little current that's flowing. And then we turn on a light pulse, and you can see the change in the current in the device. And so this light pulse has, about 10,000 photons in it. So that's what I mean by, sort of countable. We could tell that it's about that. And if you look at the number of nanotubes that are in this array, you can say that we are detecting about 40 to 50 photons per carbon nanotube at room temperature. So of course, the next thing that you do is, you say, well, I should use fewer nanotubes and reduce the number of photons I can detect. And that's exactly what we did. So this is a device with a single nanotube. It is functionalized with C60, not in this image, obviously. And in this device, what we've been able to do is to detect an absolute number of 200 photons at room temperature. So, clearly this is going in the right direction. So, but we're greedy. So we wanted to find even better systems. Oh, and by the way, the only reason why we're not detecting single photons is because of this noise in these devices. And so earlier, Sebastian showed some beautiful results on graphene using HBN. And so in that system, HBN has been very useful to reduce noise. And so this is one of the main remaining research areas in here, is to figure out how to reduce noise. But so, given that for now, we have this noise in the system, we were looking for a larger signal. And so for this, we turned to P3HT as the molecular system. And we did this because once a few years ago, it had been studied for photovoltaic type applications, but also because the band alignment is different than for C60 compared with the nanotube. So in the case of the nanotube C60 interface, what we have is that the valence band, or HOMO, I should say, of the C60 is below the valence band of the nanotube, but in the case of P3HT, it's above. And so we thought maybe this changes some mechanisms and allows us to get improved sensitivity. And so it turns out that it does. I don't have time to go into the mechanisms because they're actually quite complicated, but this is a plot of the current as a function of gate voltage for this nanotube transistor, now with the P3HT. So in the dark, you can now see that the device has an ambipolar-like behavior with a strong hysteresis, but only in one branch. When we shine light of only 500 attowatts, you can see that we can measure a significant difference in this IV curve. Okay, so obviously with this small power at which we can detect, then it makes sense to look at pulses, with a more finite number of photons. So here I show you the device that's operated in the dark, and then we apply light pulse here, and you can see this very large response of the device. And in fact, so far, we've achieved a gain here that is greater than 10 to the 9 at room temperature, and the detection of, let's say about 10 photons per carbon nanotube. So this is much more sensitive than the case of C60. And of course, this was for arrays. The next step is to do it to with individual nanotube devices to see if we're going to get the same scaling that we got previously. Okay, so what I want to do now is I want to transition in the last part of my presentation to another type of photodetector that we have currently looked at designing a new architecture for. And part of our funding comes from the US Office of Science High Energy Physics programs. And so I wanted to give you a couple of interesting examples of the need for frequency resolving single photon detection. So frequency resolving, energy resolving, or wavelength resolving. So basically we want to be able to tell what is the color of the photon that we detected. And so this is an example of the need for this. So if you're looking at liquid scintillator detectors in high energy physics, you're trying to reconstruct this detailed event, and you do this by measuring all of these particles, including photons. And you want to be able to very precisely reconstruct the trajectories of the photons. And because this is in a liquid, the speed of light depends on wavelength. So it's very important to have very high efficiency of detection, very low jitter, so you can tell precisely when the photon came, but also to be able to tell exactly when the photon arrived. I'm sorry, its wavelength. So another example comes from cosmology, where you're looking at faraway galaxies and you're trying to figure out what events are happening. And there, an example of this is to try to resolve emission lines from different reactions. So in this case, these are oxygen lines. There's two different lines, and their separation and their frequency tells you how far away the galaxy is. And so in this case, you need detectors with very high efficiency and very high frequency resolution. So just to show you the challenges and why you would want new types of detectors for this, this is the Muse instrument that is basically single or few photon spectrograph. And this is a person here, so you can see the size of the instrument that is currently needed. And so we'd like to be able to reduce this to more manageable sizes. The other way that this can be done is with nanowire detectors, superconducting nanowire detectors, but these require cooling to very low temperatures, which also makes it very bulky. So we looked at the types of designs I was mentioning earlier, where now each of the elements can be sensitive to different wavelengths. So we're still using the basic structure that I mentioned, except that now, the gaps for each of these absorbers can be different. It is still a system that does collective interaction because we need to span some bandwidth, and therefore there is some interaction between each of these elements. So just to make a long story short, we went through our design process with this, this new formalism that I mentioned earlier. And we came up with this design where you would have carbon nanotubes functionalized with quantum dots. And by making the quantum dots of different sizes, you made them sensitive to different wavelengths. So if you can make such an architecture, it would be very promising for compact single photon detectors with frequency resolution. So here's an example of this. So this is a detector that would have 12 different frequency bins corresponding to 12 quantum dot sizes. And if we send a yellow photon through the system, you can see that we have a very high probability of detecting it in the bin corresponding to the yellow photon with very little pollution of the other channels. And similarly for a green photon, and we also designed it so that if a photon comes in from outside our regime of interest, it only gives a very small probability of being detected. So with this type of detection system, you could in principle achieve 99% efficiency of detecting the photon while maintaining a jitter that's on the order of a few hundred femtoseconds and achieving a frequency resolution that would be on the order of a few tens of MeVs. So this would, of course, completely change the way that this type of detection is currently done, as I showed you, compared with these large-scale instruments. Okay, so I think at this point, I'm going to conclude. So overall, I think what we've achieved is to be able to start really from the ground up and basic physics of quantum optics to show that there are really new exciting opportunities for single photon detection, and in particular for new designs that would really surpass what can currently be done. And even though I showed you a few examples today, I think they only scratch the surface of this field of research, and there's a number of future lines of work. I've mentioned a couple of these here, but one particular aspect that we're currently exploring with collaborators is integration with high-end CMOS electronics, so we can really improve the measurement capabilities of these systems. So with this, I'll thank you for your attention and be happy to take any questions.
All right, thank you very much, Francois. Very interesting and informative. I see one question in the Q&A, Jake Mayhew. If you want, I think we can, Alex, you could activate his microphone and he can ask the question, or if not, I can ask it directly. Jake, however you wish.
Hey, thanks for a nice talk. For the carbon 60, the C60 carbon nanotube system, the responsivity versus laser power or light illumination kind of reaches up but never like plateaus, which kind of indicates that you're in a sort of saturation regime. Do you understand what causes this saturation, and do you know how this could be avoided in future devices?
Yeah, so basically, let's see if I can get the slide quickly. But and I guess I can't. But the main issue is that well, I wouldn't say it's an issue. I would say it's a feature of the system, in that when you have a very small amount of photons that are coming in, you're going to be taking a longer time basically to detect that light. So in these types of systems, with gain, there's always the gain bandwidth product. And so what happens in that case is that the gain goes up, but the bandwidth goes down. So that's the sort of issue, I guess, you would find at lower intensities. So I don't know if that addresses the question you were asking.
That was actually a similar question that I had, but I was more wondering whether if there was some engineering of like the density of states or the absorption of the C60 molecule that could like increase the point at which this transition takes place.
Yeah, so you're talking about this regime here, right?
Yeah, exactly.
Right. So so for us, we're happy with the fact that the responsivity is still increasing, but you would like to see it go up even more, right? But at that point, you run into the issue that you only have like a few discrete charges that are being created in the device, right? So in these types of array devices, if I have one charge and I have current that's flowing across many nanotubes, that charge is not as efficient in affecting transport in the other tubes that are further away. So that's why we go to the single nanotube case.
Okay, great. Thank you.
All right, looks like we have a question from Jose Ramon. Jose, if you want to ask your question, if your mic can be activated. He doesn't have a mic. Okay, I'll ask it then. So I think you showed in the transfer characteristics of your nanotube transistors some hysteresis. Does this have a big impact on the performance of your photodetectors?
Yes, so nanotube hysteresis is a well-known problem, and this occurs for reasons that are still under debate. So for example, potentially there could be water on the surface of the nanotubes, but there's also charges in the oxide that can also be creating this hysteresis. So we always need to keep very careful track of where we are operating the transistor and to make sure that we are not, in this or dominated by this hysteresis. And we can't always do that. So if you look at the case of the P3HT CNT system, you can see this very large hysteresis loop, which persists when we shine light. And in fact, this is a very unusual non-equilibrium mechanism that arises because of charge transfer between the P3HT and the nanotubes. And we, like I said, we can't always avoid it, but we can take advantage of it. And when we do this pulse detection here, what I did not show is that we actually do a very quick gauge voltage reset before, which allows us to get this large response. So it's a long-winded answer to say that, yes, it's a well-known problem. We try to avoid it, but sometimes we have to work with it.
Great. Then we have a question from Sebastian. So go ahead, Sebastian.
Yes, thanks for the nice talk. I was wondering about the carrier multiplication in the molecule. So I probably missed it what you explained, but yeah, just if you explain how you can get such large responsivity with this hybrid system.
Yeah. So basically, the reason is stepping back. Maybe I didn't emphasize this, but for single or few photon detection, it's really important to have gain. It's very difficult otherwise to detect such small events. And so the way that we get the gain here is because we are working with a transistor. So let's see. Trying to find a good example here. That's not the best. I will use this one. So this isn't perfect, but so this is the transfer characteristic of the transistor in the dark. And so if you were to plot this on a log linear scale, you would see that there's a region in here where this is an exponential increase of the current. And in that region, if you make a small change in the gate voltage, you get an exponential gain in the current. And so that's the gain of you can think of it as the gain of the transistor itself. And so when we're shining a little bit of light on it, you can think of it as we're going up on this curve. And so the gain comes from the fact that we have a single photon that comes in. It generates, let's say, one electron hole pair, right? Yeah. But we are changing the current in the carbon nanotube by a lot, and the gain then is the number of electrons in the nanotube that are impacted by this single electron, if you want.
I see. I see. But so the molecules doesn't have really I don't know, like strong absorption in particular. Just it just absorbs a bit and then transfer this this charge to carbon nanotube, right?
Yep. So the other really important aspect in single photon detection is that, first of all, the absorption has to be close to 100%, right?
I see.
So because you cannot waste anything. So that's why we're using, these thicker films of molecules, such that we're within the absorption length.
I see, and the carbon nanotube also absorbs a bit in this range. Also, this is a source of noise of.
Yeah, so the nanotube could absorb some in this this range, but we try not to rely on the nanotube absorption because it's very strongly excitonic, and a single layer of nanotubes does not absorb much light. So so that's why we try not to rely on that aspect and use the molecules instead.
Okay. Okay.
Okay. I have one question myself then, Francois. So at the beginning, you showed some modeling of how to achieve kind of these maximally efficient single photon detectors based on these incoherent transfer rates or the bandwidth if you have a crystal. So how close are these functionalized nanotubes to achieving that optimal detector performance?
Yeah, I don't think we're even close,
Okay.
or at least we don't know if we're close or not.
Okay.
Like I was saying, there are some very specific conditions between the absorption and the incoherent rate, right? So in order to tell if the system is close to that, we need very careful measurements of all of these quantities, right? And so that's really some really, detailed, optical physics measurements that have to be done. They exist in some systems, and so that's how we were able to make those predictions, for these higher level detectors using what's known in the literature. But I think what we need to do is have more of a program that has, some really basic science measurements of these quantities in these systems, coupled with, the device fabrication and so forth.
Right. Yeah. Okay.
Also have a question. I don't know if I can still ask.
Yeah, go for it.
And also, I was wondering, Francois, if it's interesting to go beyond to longer wavelengths towards meaning for the terahertz for single photon detection, or you think it's I don't know, there's first a limitation in this platform, or if it's worth to go to those wavelengths?
Yeah, so it's interesting. Absolutely, there's many applications there that could use single photon detectors. In this type of formulation, one of the challenges is the absorption process, right? So if we're using molecular systems, then at least near IR, perhaps midwave IR, it's very difficult to get molecules that will absorb. We've actually tried designing new molecules to extend their absorption into the IR, which requires playing with charge separation in a molecule and so forth. So we have a little bit of work there. I think in that direction, quantum dots are more promising because they have shown absorption in the mid-IR. If you go to the terahertz, then some molecular vibrations turn on in the terahertz, so it might be possible to take advantage of those. But those energies are very small, and the wavelength is very large. So then you have another challenge in how to couple the wave into the system, which you guys can do, for example, by using different antennas, for example, and going to the near field. But I think it's challenging to go in those directions.
I see.
All right, I see a couple more questions in the Q&A also. So one is, have you tried any other type of semiconducting nanowires, such as zinc oxide, which might lead to higher photo gains?
Yeah, so we have not looked at other types of channel materials for this. We have done work with semiconducting nanowires in the past for electronics and chem sensing and also photovoltaic cells. So I'm familiar with those materials. The one challenge is, so we like carbon nanotubes because the surface to volume ratio is very large. So that makes them very sensitive to their environment, for good and bad. Like I said, the noise is a challenge. So semiconducting nanowires could also be used for this purpose, but of course, because the surface to volume ratio is not as large, there's a question of whether that would be enough, like a single charge or so forth, to really change the conductance significantly throughout the nanowire. But certainly that could be something to explore.
I guess also the matter of finding something you can functionalize with your desired molecule is an issue as well, at least in this case.
Potentially, although people have made a lot of progress in the surface chemistry of different semiconductor materials. Silicon is a good example because they're being used for biosensing now. Okay. So, yeah.
And then the second question is if the performance depends on the nanotube radius anyway.
Yeah, so the nanotube radius, determines the basic properties of the nanotube. So whether it's metallic or semiconducting. So as long as the nanotube is semiconducting, so we need, the right properties for that. After that, the transistor. So the nanotube really sort of matters for two things. So first is the transistor properties, and the properties of the transistor depend on the band gap of the nanotube and therefore its size. So that's one aspect. And then the second aspect is that, for example, if we're using an exciton dissociation mechanism at the interface with the nanotube, then we depend on the band gap of the nanotube, which also depend on size. So at the end of the day, if you put all of this together, it could be that there is some dependence on the diameter, but I don't have quantitative calculations for that yet.
Sure. Okay. I don't see any other questions at the moment. So I think with that, we'll conclude. And François, thank you very much for joining us at such an early time for you as well.
Well,
it was a
great.
pleasure.
It was a pleasure talking with all of you today.
And thank everybody for coming. And we hope to see you in the next one as well. So have a good afternoon.
Bye. Thank you.